Hello, we will be looking at some examples of equations involving folding of sectoral structures. So we will call these folding equations. We'll start with a simple example. We have F3 of AN is equal to 4, 1 subscript 5. So what that means is we have a sectoral structure AN. We folded its third joint. So again, counting from the L prime end, we folded its third joint and we got 4, 1 subscript 5. So we will think of it just like an algebraic equation. We will multiply both sides by unfold 3. So that way we're doing a sequential process on the same joint. So we say fold 3, unfold 3 of AN is equal to unfold 3 of 4, 1 subscript 5. Of course, folding and then unfolding that joint will cancel out. Here also it's important to keep in mind that we're thinking of specifically folding a beta joint. So when you see this type of equation, this is what we saw earlier as where we specify the type of joint. So we're folding a beta joint, we're not folding an alpha joint. So then we have to do AN is equal to unfold 3 of 4, 1 subscript 5. So that means we will count the third joint in this and unfold it. And this will give us 3, 1, 1. So 3, 1 squared subscript 5. So very simple, very similar to the way we think of algebraic equations. Now let's do one that's a little bit more complicated. So here we will do simultaneous folding, and when we talk about simultaneous folding, we are referring to doing the operations at the same time. And the reason we specify this is sometimes if we do them sequentially, we will get a different result. So unfold 2 plus fold 4 of AN is equal to 231 subscript 6. So what does this mean? This means we have a sectoral structure AN, we fold its fourth joint and we unfold its second joint and we get 231 subscript 6. So to undo this, what we need to do is we need to do a set of sequential actions. So first, for the fold 4, we need to multiply that by unfold 4. So sequential on the same joint, they cancel out. And then unfold 2, we need to multiply it by fold 2 to make it cancel out. Now on this side, what we will do, and this is where it gets a little bit different than simple algebraic operations, we will multiply this side by unfold 4 plus fold 2. So basically the new operations that we added. There is a different way to simplify all of this using a multiplicative format, but I still see some benefit in doing the addition versus multiplication to indicate simultaneous versus sequential action. So fold 2 plus unfold 4 is equal to times 231 subscript 6. And what this means is we're gonna first, let's say we will fold 2 in 231 subscript 6. So go to the second joint and fold it. And that means we're gonna combine these two parts. So this will give us 5, 1 subscript 6. but we still need to unfold 4. So if we unfold 4, we get 4, 1, 1 subscript 6, or 4, 1 squared subscript 6. So this is where we see the relevance of understanding folding and unfolding of sectoral structures. Now we have this next equation, which is fold beta of an is equal to 4, 1 subscript 5 and 3, 2 subscript 5. So this one is a little bit harder because here we're randomly folding a beta joint in an, and when we do that we get one of two results. So we either get the 4, 1 or the 3, 2 subscript 5. We need to know which sectoral structure, when we apply a random beta fold to, we get one of these two results. And it's very easy to figure this out. We multiply both sides by unfold alpha. And what we will do is we will get two sets of answers. So first, unfold alpha of 4, 1 subscript 5 gives us 3 possible solutions. So if we want to unfold a random alpha joint, we have 3 possible solutions. And if we do a random, if we unfold a random alpha joint in 3, 2, we also have 3 possible solutions. And now what we need to do is find which of these are common to both sets, so the intersection of the two sets. And we will find that 2 sectoral structures meet these criteria: 3, 1 squared subscript 5 and 2 squared 1 subscript 5. So an has 2 solutions, and we can then apply the random beta folding to each of them to see if they actually fit, and they do. So there are 2 possible sectoral structures that meet these criteria. Next, we have this equation, fold 3 of an is equal to unfold 4 of beta. Of bn. So here we have 2 sectoral structures. Notice we have n and n, so they have the same degree, but they are 2 different sectoral structures, such that if we fold the first one, we get a sectoral structure, and if we unfold the second one, we get that same sectoral structure. So if we think about it, really, then to go from an to bn, we need to do 2 folding operations. So we can say fold squared or fold beta squared of an is gonna give us bn, so 2 foldings. However, this is given to us. This is not something we concluded. And the reason is it's given to us is because it wants to show us that when we do 2 random beta folds on a sectoral structure, we usually get a set of answers. But here it's telling us that there's really one answer only. Additionally, what's given to us also is that a random is that the folding of bn will give us bn. So if we fold bn, it gives us bn. What sectoral structure has this criteria? That if we fold it, we get the same sectoral structure, and that will have to be a theta structure. So it's already fully folded, so if you try to fold it randomly again, you get the same sectoral structure. So we already know bn is a theta structure. Now let's go back. We're going to use the folding polynomials in this case. So we know f3 of an, we will write this as 3, so x minus 3, because it's the third joint, and since it's folding, it's raised to the power of 1, times a, which is the sectoral structure, is equal to x minus 4, so unfold 4 to the negative 1 of b. And we also know that, I mean, we could solve this directly, but we also know that um, doing two foldings on AN gives us BN. So we will say X minus S, so a random joint S, we are folding it, times X minus T, a random T joint that we're folding of A is equal to B. Now we're gonna substitute into this second equation, no, actually into the first equation, we will substitute B by this expression here because it's already equal to B. So what we will get is X minus 3A is equal to X minus 4 to the negative 1 times B, and instead of B we will say X minus S, X minus T, A. So notice what we can learn from this equation. So we have A here and we have A here. So that what we can tell is that this operation before A is equivalent to all of this operation before A. So therefore, if we simplify all of this, it should give us X minus 3. So how can we think of this? To begin with, we have X minus 4 to the negative 1 that we need to get rid of. And in order to do that, we will multiply it by this next expression, X minus S. And to get rid of it or to simplify it, then X minus S must be the reciprocal of X minus 4 to the negative 1. Therefore, this tells us that S is equal to 4. So this will be X to the negative 4 minus 1 times X minus 4. It cancels out. Then we are left with X minus T here and X minus 3. Therefore, we know that T is equal to 3. So now this really helps us see it in a more algebraic manner. Now, we can go back and substitute this as follows. To go from AN to BN, first we need to fold 3, so F3. And now we also know that we need to fold 4. So we will say F3 plus F4, we got 3 and 4 from here. So F3 plus F4 times AN is equal to BN. And we already know that BN is a theta structure. So we will simplify this expression to F3 plus F4 of AN is equal to theta N. Therefore, if we want to solve for AN or simplify this, we're going to have to multiply these sequentially. So F4 will be multiplied by unfold 4 and F3 will be multiplied by unfold 3. And therefore we will say AN is equal to unfold 3 plus unfold 4 times theta N. If it's easier for you to get rid of the plus signs and just make everything multiplicative, that's also fine. The distinction is somewhat, it does exist, but it's a very small distinction between the two. Anyway, so AN is equal to unfold 3 plus unfold 4 of theta N. So we still don't know what theta N is. However, we'll see how using sectoral structures we can solve this much easily. We will say AN is equal to, if we're unfolding the third joint, that means the first two sectoral structures are joined, and then the third sectoral structure is still joined to them. We're at the second joint here. And then the fourth sectoral structure will not be joined. So that's where it will be separated. The third sector, not sectoral structure. So if we're unfolding 3, That means the first three sectors will still be joined, and then after that we do the unfolding. So we will say an is equal to 3, comma. We're also unfolding the fourth joint, so there's going to be a 1 here that's on its own, a single sector. So we have 3, 1, and then the rest of this will be n minus, which is the degree, minus 3 minus 1. So n minus 4. So we've already really figured out the general form of this sectoral structure. So an will be 3, 1, n minus 4 subscript n. Now keep in mind that n minus 4 must be at least 1 for this to be a sectoral structure. So n minus 4 is more than or equal to 1. And when dealing with sectoral structures, the 3 here must be the L prime n, because we have those in standard form. So we know that n minus 4 must be less than or equal to 3. If it's 3, then it's symmetric. If it's less than 3, it's just a non-symmetric sectoral structure. So n minus 4 is less than or equal to 3, therefore n is less than or equal to 7. And n minus 4 is more than or equal to 1, therefore n is more than or equal to 5. So therefore n is either 5, 6, or 7. These are the solutions. So an has 3 solutions: 3, 1 squared subscript 5, 3, 1, 2 subscript 6, and 3, 1, 3 subscript 7. So perhaps when we first saw it, it wasn't obvious that it had very clear solutions, but now we see that it does. So we can say an is this is the set of solutions, and bn is going to be one of 3 theta structures: 5 subscript 5, 6 subscript 6, and 7 subscript 7. Similarly, we will say that we will take a new example actually. So we will say that unfold 1 plus fold 2 plus unfold 3 of an is equal to the conjugate of an. To do this, we need to remember what a conjugate is. So a conjugate of a sectoral structure is basically taking every joint and reversing it. So a beta becomes an alpha, and an alpha becomes a beta. In other words, it's a series of folding and unfolding operations. So if we know that this set of operations is equal to the conjugate of an, this tells us a lot of information. We already know that an and its complement, both of them have 3 joints. So we'll say j of alpha plus beta is equal to 3. And if we know that it has 3 joints, then it must have 4 sectors. Therefore, the degree n is equal to 4. We also know we can figure out the number of beta joints, because to go from an to its complement, we have to fold a single joint. Therefore, we know it has only 1 beta joint, and this means its order lambda is equal to 2. And this way we can figure out what each joint is. So the first joint, to go from an to its complement, we have to unfold it. So therefore that's an alpha joint. The second joint is a beta, and the third joint is an alpha. So we can write this in the extended notation. If you remember, we saw this earlier. So this is 1 continuous with 1, alternating with 1, continuous with 1. Wherever we have the alternating, we put a comma, and the continuous, we add them. So this is 2, 2. So 2, 2 subscript 4. This is AN. And similarly, we can figure out its conjugate based on this by flipping all of these joints, and we get 1 to 1 subscript 4. So if we have a set of folding operations of AN on AN that give us its complement, then we can write this in a different way. So this is a different way to think of the complement operation. And usually we just put this dash over it, but we can think of it as an operation where we unfold all the alpha joints while simultaneously folding all the beta joints. So we will say unfold all alpha plus fold all beta of AN gives us the conjugate, sorry, I was saying complement, it's the conjugate of AN. So let me repeat that one more time. So the operation that takes us between the sectoral structure and its conjugate is the operation unfold all alpha plus fold all beta simultaneously. Thank you.